100. This video is one that I look forward to putting up because this is where I kind of think we go in to big boy, big girl statistics. And I don't necessarily mean that it's harder. In fact, I think this is probably some of the easier part of the course. Some of the theory, some of the reasons that we do things, the underlying the underlying theory is a little harder, but the way we do these problems on our calculator and on R actually turned out to be to be much easier. So at least I think it's definitely easier than the central limit theorem. Good news, I guess, is midterm exams are behind us. That's really good for some of you. Because some of you did very, very well in the midterm. Others of you not so well. And I would take this as a indication that if you are a smiley face right now after getting your midterm report, then or your midterm exam score, then just continue to do what you're doing. And I'd say most of you that are doing well, you're watching the videos, you're doing what I'm asking you to do. If you fall over here and you've got the sad face, then that tells me that what you've done the first half of the class isn't working for you. And I'd say more than likely, you're either not watching the videos or you're not watching them intently enough. Guys, I know this is going to sound conceited and cocky, but I don't care. I know what I'm doing. I've taught this class over 100 times. I know what I'm doing when it comes to teaching statistics. And those of you that are trying to not watch the videos and just log on to the online course management system and do the assignment questions only, it's not going to work for you. And I explained that earlier. And some of the questions that I'm getting from the email that I get just show me that you're not approaching this class the way that I told you need to approach it. So, and what's going to happen? You're going to waste your money. You're going to end up taking statistics again because you're going to fail at this time. Guys, do what I ask you to do. I'm asking you to watch about 2 hours of videos a week. I'm asking you to put in about an hour or so, on your homework assignments. Less time than you would spend if we were meeting in class. So anyway, enough of my ranting and raving. It's just I am committed to student success, and I'm holding up my end of the bargain. I'm putting up these videos that clearly teach you what I want you to learn. I'll let you use some resources on the first exam that I usually don't let my students use. So I'm doing my part, but I'm convinced that some of you aren't doing your part, and it's frustrating to me because I don't know how many people we've got in this class, but I want all A's. I'll be honest with you, but I get frustrated when I don't get that. So anyway, let's just put all that behind us. You still have over half of your grade yet to be determined. So if you fall in this over here, then you still got plenty of room to improve your grade and get through the course successfully. All right, gang, what we start today is Intro to Inference. And when I talk about inference, what I mean there is we reverse what we've talked about so far. Now, you've seen this silly drawing ad nauseum. But it's not a silly drawing. It's a very helpful drawing. What we've done so far is we have worked on this direction where we have a population information that's given, and let's say we might say that we know that IQs are normally distributed with a mean of 100, standard deviation of 15, and we can use what's called probability. Well, probability, okay, I can spell, I just can't see. We can determine probability, use probability to determine the likelihood of getting a sample that's unknown. Now, what I mean by unknown is if I close my eyes and choose a sample from this population at random, I don't know what I'm going to get. But I can determine the probability, for example, that I get someone with an IQ above 120. I can determine, for example, that if I choose 50 people out of here, that their mean IQ will be above 105. So I can determine probability based on an unknown event. Now, the reverse is what we focus on today, and what's given and what's ungiven reverses also. What we do in this part is we start with a known sample. So we start out with a mean, a sample mean of a certain value. We have a certain standard deviation of a certain value. Guys, sometimes we have the luxury of knowing the population standard deviation. It's rare, but that's the way we're going to start because it's a common way to start. And what we end up over here, we're trying to estimate a value that is unknown. Now, for example, what if I would like to know the mean IQ, the IQ for all nurses? So that's what I'd like to know. Does anyone know that? No, you don't. It's unknown. But I'd like to estimate it. And what I would do is I would use inference. So I would go out and I would collect a sample. And let's say I collect a sample of 50 nurses. And I get a mean of 112 and a standard deviation of 11. I can use this information using inference techniques to make an estimate on the unknown value from the population. So that's what we're going to be doing. We're going to be looking at a specific case, okay, today, and I'll explain a specific case here in just a second. Now, let me tell you what's coming up in terms of your assignments. You'll see your assignments are posted on the online course management system. Your first assignment, well, I've got the due dates set on Hawks, and as always, the time these things are due at 11:45. So just log on to Hawks, and you'll see that you've got one assignment. I think the due date's coming up fairly soon, but then I give you a couple of extra days on the second and third assignment. So, I forget exactly when I made those due. So just log on and onto the page, and you'll see the due dates. Okay. Well, the purpose of this assignment is to get you ready to do the first the first assignment, and it helps in getting ready to do these problems to revisit the central limit theorem. And the central limit theorem says what? We start with a population where the mean and the standard deviation are given. If we have a normal distribution, then all we need is a sample size of 2 or bigger. If we have a positively or negatively skewed distribution, we have a little bit more restriction on our sample size, and we need 30 or bigger. If this is met, the next thing we did in that part is we begin our random samples. So we set in, and just for talking this through, let's say we set in equal to 50. Now guys, I'm still back here in looking at the sample and the population. Right now I'm still back here in this direction. But what I'm doing is I'm setting the foundation to look at this direction. So anyway, the central limit theorem says we set our sample size at 50, and then we start taking random samples. So I dive into my population, I pull out 50 measurements, I add them all up, divide by 50, and I get my sample mean of my first group of 50. I do that again, I do that again, I do that forever. Now, guys, what we call that is the distribution of sample means. And the central limit theorem tells us that these numbers will be normally distributed. It tells us that the population mean of these numbers will be equal to the mean that we started with way back here. And it tells us that the standard deviation of those numbers will be sigma divided by the square root of n. Now this is for quantitative data. We'll get into categorical data here in a couple of weeks, but this is just for the quantitative data. Now, what I want you to think is let's switch gears from probability to inference. Inference, what do? We select one sample. Now, which one is it back here? Is it the first one? Is it the second one? Is it the third one? We have infinitely many of these, but we come in and we choose one of them. So let's just say for the heck of it that we know that it was the 1,117,432nd mean that we selected at random that we want to use to estimate mu. This is known. It's the one at the 1,117,432, whatever I said. I forget now. It's irrelevant. But this is unknown. And let's just say for the sake of example that we want this to be the IQ, or I should say the average IQ of all nurses. So I go out and I collect 35 nurses at random. I give them all an IQ test. And I find out that their IQ, mean IQ for those 35 is 112. Now, it's ridiculous. It's not even logical to say, well, therefore, I must know that my average IQ for all nurses is 112. Guys, that is not true. The average for these 35 is equal to 112. There's no reason to think that we just happen to luck up back here and get the one sample mean out of infinitely many that represented this value right here. It's not even reasonable to think that. These things vary, hence we've got variation that's described in the standard deviation, the standard error. These things fluctuate. There's infinitely many of them. Why would we think that we got the perfect one? Well, we don't assume that. So what we do is we assume this x bar equal 112 in this case is our point estimate. And what we do is we provide margin of error, margin for mistake, based on a variety of factors to estimate this value that mean is the value that we're actually looking for. And that is, again, mu, which is the population mean, which is unknown. So guys, at the end of the day, what does the central limit theorem tell us? Central limit theorem tells us if we could take all of the sample means, we would have what's called the distribution of sample means. And smack dab in the center of this would be mu. Typically, at least in the past, that was known. But now it's unknown. But we do know that the distribution or the variation around the mean can be seen as the mean plus a standard deviation, the mean minus a standard deviation, the mean plus 2 standard deviations, the mean minus 2 standard deviations. I could go on to 3 above and 3 below if I'd like. But guys, in these problems, our standard deviation is given as sigma divided by the square root of n. So when we have our sampling distribution, smack dab in the center is the mean. One standard deviation above is sigma over the square root of n. Mean minus sigma over square root of n. Plus 2 over times sigma over square root of n. minus 2 sigma squared over n. And we know that based on the 68, 95, 99% rule, that 99% of our sample means will fall between these two values. Now, sort of. Guys, it's kind of been a little, I haven't lied to you. We say that in all statistics classes, whether they're taught at Shawnee State or at Harvard. We say that between 2 standard deviations below and 2 standard deviations above, that 95% of our distribution will fall. Well, that's a little fuzzy math there, and that's not actually completely true. So let's see what exactly is true. And let's get better estimates. Now, the first thing that I want to calculate is I want to calculate my Z critical based on 95% of the distribution between two values. So guys, the way I'm going to do that, and guys, this is super important because this is going to set the stage for some stuff coming up. Between what two Z values? We know one has to be positive and one has to be negative because Z values, we know the mean is equal to 0. Does 95% of our distribution fall? Well, the way we do this is we use the inverse norm. If we have 95%, we know that 5% is missing. We know half of that 5% has to go right here. And we know the half of the 5% has to go up here. So I've got 2.5 and 2.5 is 5. Plus the 95 gives me 100%. So I have everything that's accounted for. Now what I'm going to use is I'm going to use my calculator and use the inverse norm. Now what goes first? Percent below, right? Well, I need 2.5% below, so I have 0.025. The mean is 0. Standard deviation is 1. So I have negative 1.96. Now, I should know, if you've been with me, you should know that this is positive 1.96 because of perfect symmetry. But let's say that you just don't see that, okay? And you want to use your calculator to verify that. Well, guys, what I would do is I would go inverse norm again. I need percent below from this point right here. Well, I know that I've got 95% below to here, but I've got this additional 2.5, so I need 97.5% below, and I get positive 1.96. So I really didn't need to do that because once I get one of these at negative 1.96, I know that this one up here has to be the positive. So we know that a better estimate instead of 2 is plus and minus 1.96. So guys, what that tells me, and I'm going to come back to this because I want to work on some more stuff here. What that tells me is in the distribution of sample means, that smack dab in the center is this value that I don't know what it is, but I know it's centered at this value I'm looking for, I'm trying to estimate. 2 standard deviations above, no longer. We see now that 1.96 is a better estimate. Negative 1.96 is a better estimate down here. That 95% of our distribution falls between these two values. this value, and this value. Now, what if I wanted to focus for some reason on 90%? Well, guys, how would I work that problem? Well, just like before, it worked for 95%, so let's do the same thing for 90%. What did I do? I sketched the normal distribution real quickly. Doesn't have to be pretty. I drew two lines, and I want, instead of 95%, I want 90%. Now, what's the next question I ask? How much is missing? I've got 100% total. So I've got 10%. What did I do next? I divided that by 2 because I want to put equal amounts here and here. Convert to a decimal. So I know that I have 5% here, 5% here, and just mental arithmetic tells me I've got my 90 plus my 5 gives me my 100%, which I always need. Now, how am I going to find this value? Just like before, calculator. You guys that are fighting me on these calculators, I don't understand it. I really don't. But you're going to do what you're going to do. There's nothing to do about it. So what I want right here, I want this. I want percent below, which is 5%. I got to put it in as a decimal. So I get negative 1.64, and that's a close call out here. So I'm going to go out to 3 places. But I know this is negative 1.645. This has to be the positive of that. Okay, let's say I don't believe that. I believe you're pulling one on me. Well, let's just do it. Start right here. We got 90% plus the 5%. And I get the same thing, the positive. So guys, when I go back over here, I'm going to complete this chart. Better estimate if I want 90% centered in the distribution. I'd have 1.645. Let's do one more. These are so much fun. Let's do 99%. So what are you going to do? Well, you're going to learn from the past. You're going to let me teach you. I want 99%. How much is missing? %. Divide by 2. 0.5%. 0.5% is a decimal. Is 0.005. Move your decimal place 2 places to the left to convert a percentage to a decimal. 2 places to the right to convert a decimal to a percentage. Okay? So I have 99% here. What do I have here as percentage? 0.5%. And 0.5%. So I have my 99 plus a half plus another half gives me my total 100. Now, to find the z value that goes with this, what am I going to do? Inverse norm. 0.005, comma 0, comma 1. So again, kind of a close call there. 5, 7, 5, 8. I'm going to go out to 3 places here at negative 2.576. So I know the other has to be the positive of that. Now I want to pull in something just kind of random. What if I want 60%? Do the same thing. Put that number in the middle. How much is missing? 100 minus 60 gives me 40. Divide by 2. 40% divided by 2 is 20%. I want 20% there. I want 20% there. 60 plus 20 plus 20 gives me my 100. I'm set. Use my calculator. Now to get this point right here, what I need, percent below. What is it? It's 20%. Negative 0.84. This one has to be positive 0.84. Well, boys and girls, these numbers that I'm creating are more than just an academic exercise. It turns out that we're going to get into what's called estimating with confidence. This is going to be what we call a confidence level. And this is going to be what we call a Z-critical, which we sometimes denote as Z star. So these Z-critical values are going to become very, very, very critical. Sorry. In us being able to create these confidence intervals, estimating with confidence. So guys, this stuff right here, you're going to need to tattoo to the brain. And you're going to need to know how to create these values for other levels of confidence. And I'm going to illustrate that a little bit later. All right, gang, let's get to the good stuff. Well, our papers are all bunched up. All right, gang, here's what's going on. We set in to be 30. We start drawing samples. What do we call this? The distribution of sample means. Central limit theorem tells us that the distribution of sample means will be normally distributed. Smack dab in the center will be the population mean. For us, this is unknown. We know that 95% of these sample means will be between mu minus 1.96 times the standard deviation over the square root of n. I'm sorry, I said that wrong. Mu minus 1.96 times the population standard deviation divided by the square root of n. Remember, guys, we call this a standard error. And up here we have the mean plus 1.96. Now, we come in and choose one of these at random. Let's just say the one we got at random was right there. It could have been that one. It could have been this one. It could have been this one. But let's just say for the sake of illustration that this is the one that we got. Now, if we take that interval, because that's ultimately what we got. We start here at the mean mu, which we don't know. There's a distance from here to here. If we take that distance instead of centering it at mu, let's take this and center it at x bar. Will this interval that we created contain what we're looking for? Yes. Now, what if it had been this one? So let's take this, let's take it and center it. You can't see my left finger, but it's over here, okay? Does this interval contain what we're looking for? No, it does not. But we know that 95% of the sample means that we could get, as long as they fall between here and here, for just very simple geometric reasons, that if we build an interval around this value, what we call a confidence interval, that it will contain what we're looking for. So guys, if I have X bar in the center, what will this left endpoint look like? Well, the distance from here to here is found by subtracting 1.96 times the standard error. So it should make sense that that distance is the same as that distance, just shifted over. So it would make sense, therefore, that that left endpoint is found as this. What's this one going to look like? Well, the distance from there to there is by adding 1.96. What's the distance from there to there? It's still by adding 1.96 times the standard error. Will this interval contain mu, what we're looking for, what's unknown? It will, as long as we randomly selected an X bar between here and here, which we had a 0.95 probability of doing. We'd have to get something out in here, which is rare. Only 2.5% of the sample means are from here out, and 2.5% are from here out. So we'd have a really, really unlucky day if we happened to get a sample mean that was way out here, which only had a probability of attaining of about 1%. Even less here, even less here, even less here. Anything to the right of this line right here would be rare. It would be rare to get a sample mean that one. But you could get it, but it would be rare. You could go to, I was in Las Vegas, I don't know, 7, 8 years ago, and somebody at Bally's hit one of the slots for like, I forget, something crazy, like it was like 20 million or something insane. Well, the probability of doing it wasn't very high, but it happened. But I don't think people want to go to Las Vegas and rest all their hopes on something that unattainable. It can happen, but the probability is awful low. Could you get a sample mean right there? It could happen. But the probability of getting a sample mean higher than that would be extremely low. 95% of the time, you're going to get a sample mean between here and here. For example, if it's that one, we can shift that interval, and what we're looking for will be contained in that interval. Guys, these two values right here take on a very, very, very special meaning. X bar minus 1.96 sigma squared of n, X bar plus 1.96 sigma squared of n. We can put that together to create what's called the 95% confidence interval for mu. Why are we specifically focusing, got a lot of papers here, guys. Why are we specifically focusing on the 95%? Well, that's just what I chose. This 1.96 is the Z critical for the 95% confidence interval. What if I wanted any confidence level? any percentage confidence interval. Then I use the sample mean, plus or minus the z critical that goes with that confidence level, times the standard error. So guys, let's give these names, okay? This is our sample mean, or our point estimate. This right here is called our z critical. This right here, the total thing, is called our standard error. All of this stuff over here that I'm boxing in is referred to as our margin of error. All right, gang, let's get our hands dirty. Let's get some, let's jump in full-fledged, all right? We'd like to estimate mu. What are we going to do? We're going to collect a random sample. Let me get, all right, came up something about installing a new update or something. So let's say, just for the heck of it, that we dive into our population that has this mu that's unknown, and we created a sample size. We took out 30 observations. The sample mean that we got was 92, and we know that the population standard deviation, for some reason, we know that from previous studies is equal to 8. Now guys, this is a sample statement, this is a population statement. It's a little weird to have that, but that's the way we start these types of problems, is assuming that we know the population standard deviation. And let's say we know that. So I'd like to construct the 92% confidence interval. Now, I'm going to first of all show you how we do this with the formula. The formula is x bar plus or minus c critical times sigma over the square root of n. We have 1, 2, 3, 4 things we've got to know. Our sample mean is 92. Our z critical, we don't know yet. We'll have to come back and get that. Our sigma is 8. And our sample size is 30. Now, how do we get this z critical for the 92% confidence interval? Just like before. How much is missing? 8%. Divided by 2. 4%. So that tells me that in my picture here, draw it real quickly, doesn't have to be pretty. %. How much is missing? 8%. Put half of it. Put half of it. So I find this by going distribution inverse norm. 0.04, comma 0, comma 1, just like before. 1.75 is my z critical. Now that's my z critical for the left one, but we know that the plus and the minus comes from the fact that we have a symmetric distribution. So gang, let's put this in our calculator. So we're going to have, I'm going to clear this out. So I'm going to do plus or minus, just tells me I got 2 things I got to do. Typically, or you know, in arithmetic, it's not even math really. if I have something like, 8 plus or minus 5, this just tells me that I have two statements that I have to work. I have to work the 8 minus 5, and I have to work the 8 plus 5 right here. Two of them. Got to work them both. Okay? So that tells me here I've got to work them both, but guys, get in a habit of working the negative first. And I'll explain why in just a second. So I'm going to have 92 minus 1.75 times 8 divided by the square root of 20. So I have 88 plus 0.87. Guys, I'm going to show you something kind of cool. If you'll just go, let me put it up here where you can see it. If you'll just go second entry, it'll bring exactly what you typed. All you got to do is go over there and change that to a plus, because that's the only thing you need to do. You need to do the plus and the minus. So our 92% confidence interval is going to be 88.87 to 95.13. Now, sometimes this is written differently, and your textbook does that. It will write 88.87 less than or equal to mu. These two statements are saying the same thing. The interpretation, we will say there is a 95% probability that this interval contains mu. Oh, that's not right. We didn't do 95%. Not bad. We did a 92% probability. Got sloppy there, boys and girls. Because, again, think back here. We wanted to estimate 92. I wish I hadn't used 92 and 92. That kind of, that don't get confused. Those will always be the same. In fact, they're completely unrelated. All right? Now you want to see the easy way? And guys, remember our calculator, our answer was what? 80. 8.87. Now you talking about easy. This is worth the price of admission. I feel sorry for you, those of you who have gotten frustrated with the video or maybe tired of listening to me and aren't watching. Well, guys, what we're doing here is called a Z interval. And a Z interval is what we use when mu is unknown. We want to estimate mu at a certain level. Well, guys, I'm going to tell you what. This is where it gets fun. Okay. Now remember, what do we know here? We know that we calculated a we collected a sample size 30. We know that the sample mean was 92. We know from previous studies that the standard deviation of the population was 8. And we wanted 92% confidence. All right, so here's the way you would do that, guys. All right, hit your stat key. Scroll all the way over to test. And scroll down to number 7, which says Z interval. Now, you got a choice here of data or stat. Now, if we had these 30 numbers typed into a list, we would go over here to data and we would select it and we would tell the calculator where the list of numbers, what list we typed the numbers in. Guys, we don't have that here. We've got the statistical results. So the first thing it asks us is what is sigma? Well, that'll be provided in the problem. The next thing it asks us x bar, which in this case is 92. The next thing it asks us is the sample size. And the next thing it asks us is the confidence level. Now the confidence level is 0.92, or you can just put in 92. Either way, it's going to work. Your calculator is going to work. Guys, hit calculate. What's going to happen? You're going to see something. Oh, wait a minute. What happened here? Huh. I know what happened. We got a rounding issue. All right. Now, let me show you what happened there. I'm kind of glad that came up because, well, just let me show you what happened. We did a 92% confidence level up here, and we're off a little bit. In fact, we're off quite a bit. So what happened there is because we rounded the z critical. So I'm going to show you how to calculate this a little easier. That doesn't seem like it should be off that far. Let me try one more thing before I make sure I didn't make an error. So standard deviation was 8. Sample size was 30. Sample mean was 92. And all right. I have to admit, I'm kind of surprised that it was off that much. Well, that's frustrating. I'll tell you, this is a better estimate, but let me show you what actually happened. So with the calculator, we actually ended up getting 89.44 to 94.56. Now let me show you what happened. Let's focus. How did we not get that? What happened is when we did our z critical. So we're at the 92% confidence interval. So again, we got 100 minus 92 is 8 divided by 4. I'm sorry, divided by 2 gives us 4%. When we did this right here, inverse norm at 0.04, comma 0, comma 1, I got 1.7506. Now, what I want you to do is I want you to write that out further. So I want to take now my 92 minus 1.7506.86.071 times the standard deviation of 8 divided by the square root of 30. Look familiar? Now we get the 89.44. The reason we were off is when I put this in at 1.75, I got a rounding error. And usually it won't be off that much, but this was off quite a bit from 88.87 to 89.44. So about 0.57 units. If I go second function entry, I'm going to get everything but the positive of that. So I don't have to type everything back in. And I'll see that I get my 94.56 here instead of the 95.13. So what we got into was a rounding issue. Now, instead of typing all these, I don't know how many, 1, 2, 3, 4, 5, 6, 7, 8, 9. Instead of doing that, we probably could have gone out to about 5 units, 5 places, and been okay. Or, better way to do it, just use your calculator. Use stat test, Z interval, type in your information, and it calculates, and you don't have any rounding errors. Okay? All right, gang, let's work some problems. What I'm going to do from here on out is I'm going to try to make my problems I work in this video look more like what you're going to see. Guys, hold on. I got somebody at the front door probably getting a package. Be back in 2 minutes. All right, guys, sorry about that. Never fails. All right, guys, we'd like to estimate the mean wait time for drive-through customers at Wendy's in Portsmouth. I don't know a lot about, I've worked here 21 years, but I don't even know. Hopefully Wendy's has a Portsmouth location. If it doesn't, pretend it does. Insert any restaurant. So we go out and we decide that we're going to collect a random sample of cars waiting in line. So we decide that we're going to, for one reason or other, do 42 cars. And we'd probably want to do this for 42 randomly selected cars, maybe over a year. I don't know how we do that, but and we see that the mean wait time for these 42 cars is 2.8 minutes. From previous literature, we see that the population standard deviation wait times for all restaurants is 0.9 minutes. With 0.95 confidence, estimate mu, which is the average wait time for all drive-through customers at Wendy's in Portsmouth, Ohio. Now, what are you going to do here, guys? If you've got the flexibility of working this problem however you want, what are you going to do? Dude, I'm going to pick up my calculator. I don't know about you. I'm going to do it the easy way. I'm going to go to stat. I'm going to go to test. I'm going to come down to Z interval. And I'm going to put my information in. Sigma is 0.9. X bar was 2.8 minutes. My sample size is 42. And my confidence level is 95. That is what I said, right? Yeah. And I'm going to report my 95% confidence interval is 2.53 minutes. To 3.07 minutes. Now, gang, a lot of times I'm going to ask you to find what's called the margin of error. And the margin of error can be found. Again, let's write our 2.53, 3.07. To find margin of error, we can do one of two ways. First of all, we can use what's called the divide by 2 method. This is a Darboism. You're not going to see this anywhere in that crease right there is driving me crazy. But anyway, the margin of error, which I will just call ME here. The divide by 2 is we take the big number. So you've got to know your confidence interval to be able to use this method. Subtract your small number, 2.53, divide by 2. So 3.07 minus 2.53 divided by 2, we get a margin of error plus or minus 0.27 minutes. All right. Another way to is use the formula. Now, guys, I'm going to have to go back all the way through my notes here someplace. Hopefully, it's not too far. But I gave you the formula. I think it's right here. Yeah. I gave you the formula for the confidence interval for any percentage. And I told you that the margin of error was everything in this box. So plus or minus z star sigma squared of n, we can calculate the margin of error using the formula. Now, this is the easiest way, but sometimes we have to calculate the margin of error. Using the formula. So using the formula, what's the z critical for the 95% confidence interval? 1.96. Our population standard deviation was, I think it was 0.9, but I forget. Yeah, 0.9. And we have a sample size of 42. Now again, plus or minus says I have two things I got to do. Got to do the plus, got to do the minus. These guys need to go to the home screen. Let's get rid of everything here. So I'm going to do the, really I don't need to do anything. I just need to do the numbers and then just put a plus or minus in front. So 1.96 times 0.9 divided by the square root of 42. And I get 0.27, okay? So I didn't get any rounding issues there, and you know, typically you won't because and quite frankly, we rounded these numbers to 2 places. So rounding this to 2 places, we shouldn't get much of a problem working problems like this, okay? But as we saw before, when you calculate your own z critical, you have to be extremely careful with rounding issues. All right, guys, going to work some problems. I just spilled my coffee. Good job, Douglas. Wow. All right. Shoot. All right, let's review a little bit. I'm going to bring this just a little bit closer. Some of you said that it'd be helpful if it was just a little closer. So, guys, our focus here has been estimating a population mean when the population standard deviation is known. We call this technique a z-interval. We can use our calculator to find z-intervals, or we can create z-intervals using the formula. What's the formula? And what's the cautionary tale here? If we use the formula, make sure that we take the C critical out far enough to where we don't get into a rounding issue. Now in the next video, I'm going to show you how we handle estimating a population mean when the population standard deviation is not known. And these turn out to be a little bit harder. That's the reason we start with these, which are easier, before we get into the harder ones. We get into what's called a completely different distribution called a t-distribution, which depends on degrees of freedom and so on and so forth. But I'll teach that to you soon enough. Confidence intervals are presented two ways. They can be in classic interval form, or they can be in this form right here. Regardless, we call our sample mean the best point estimate. So our best point estimate is the value we get from our sample, which we are using to try to estimate the mean. All right. So gang, let's do some problems here. First one says a sample of 300 women is selected to examine purchasing habits. Construct a 76% confidence interval for the number of dresses purchased each year. If the mean is 4.2, the population standard deviation is 1.8. This alone tells me that we use a z-interval. Again, I'm going to teach you something upcoming called the t-interval. So work the problem using the formula. All right. Not going to be hard to do. All right, so let's do it. So using the formula, we have x bar plus or minus c star over sigma divided by the square root of n. Our sample mean is 4.2. Our z critical we have to calculate. So let's think about it. Start out with 100. Subtract 76. Divide by 2. So I need 12% on, okay, just got a phone call. I need 12% on each side. So I'm going to go second function distribution, inverse norm, 0.12, comma 0, comma 1. So my, and I want to go out so far, so I'm going to go 1.175, so on and so forth. My population standard deviation is 1.8, and we have 300. All right, gang, if I'm going to put that in my, use that in the calculator, I'm going to type in 4.2. Do the minus first. I'm going to go out pretty far. 7, 4, 9, 8, 6, 7, 9, 1 times 1.8 divided by the square root of 300. Go second function entry, which again, if you don't know the entry, it's right there. That's a blue, so I have to hit my blue key first. Let me do the, all right, that's a little better. So the only thing I need to do is just change the negative to a plus with a plus minus. So my confidence interval is going to be 4.08 to 4.32. And again, that could be rewritten. Again, either one of these is going to be okay. Now, next thing, work your problem using your calculator. And this is really cool when you get to do this. I mean, really cool. Some people are saying, oh, I didn't buy a calculator. Well, you messed up. Told you day one was needed. All right, so standard deviation was 1.8. Our sample mean was 4.2. Sample size was 300. We wanted to estimate with the 76% level of confidence. And guys, because we rounded out this Z critical, you can see that we have 4.08 and 4.32. So the numbers do work out perfectly. Using the same information, construct a 95% confidence interval. Well, this is kind of cool here because it doesn't tell me how I'm supposed to do it. So if I don't have directions on how I'm supposed to do it, I'm going to do it the easy way. All the information's the same. The only thing I need to do is change that to 95. And my so the 95% confidence interval is 3.996. So that would actually round to 4.00 if we're doing it to two places. And 4.40. Now, I don't think I asked this. Yeah, I did. What's the margin of error? Well, I will calculate the margin of error for both because I want to make a teaching statement here. So let's do the margin of error for the 76% and for the 95%. Okay? So guys, the margin of error for the 76%, I'm going to take the high number minus the low number divided by 2. So I get plus or minus 0.12. And for the 95% confidence interval, I'm going to take the big number minus the small number. And I get plus or minus 0.2. Notice that the margin of error is bigger for the more confidence I have. So the confidence interval for the 76% is not as wide as the confidence interval for the 95%. The reason being, I have more confidence that this interval contains mu, so I have to go wider to get more confidence. It's kind of like if I'm if I'm estimating the mean age of all of the students in my Math 1500 level class, how much confidence can I say that the average age of you guys is somewhere between 0 and 100? Well, I am completely confident. I could go all the way out to the max and say I'm 100% confident because I went so ridiculously wide with my margin of error. My margin of error there's 50. 100 minus 0 divided by 2. But how much confidence can I put that your average age is between 21 and 22? I don't know. It's possible. But I can't be as confident because my margin of error is smaller. So when your margin of error is smaller, you have less confidence. When your margin of error is higher, you have more confidence because you've gone wider on your confidence interval that's being used to estimate what's unknown. Now, what's the margin of error divided by 2? Well, guys, we just did that, okay? 0.20. All right, guys, this is a little bit harder problem, but there's a couple on your... I don't think I have any paper left. Shoot. Yeah, here we go. It's kind of crumpled, but we can use this. So we'd like to estimate the mean IQ for professors at SSU, and we'd like to ensure that our estimate has an error. Now here, guys, error equals standard error. Actually, it doesn't in this context because we're doing 72. So this actually represents the margin of error. Okay? So to ensure that our estimate has a margin of error of at most 1.5 at the 72% level of confidence. Previous study reported the mean to be 112.85 with a standard deviation 13.76. What is the minimum sample size required to ensure the desired level of confidence? Well, guys, this is a situation where we have no choice in dealing with this problem and using the margin of error formula. Okay? Now, I'm going to, because it's going to make things much easier, we don't need to deal with this whole plus minus thing. We'll just put in the Z star. Don't need to worry about that plus minus. That creates two problems. It's not going to help us in solving for a sample size of n. So we're just going to look at the positive part of it. I want my margin of error to be at most 1.5. My Z critical has to go with the 72. Let's do that real quickly. How do we do it? 100 minus 72. That's how much is missing. Divide by 2. 0.14. So I need 0.14 below. So it's, let's just call it 1.08032. I'm going to go up 5 places, and that's usually enough. Again, you can see. And then I have sigma, which we know in this problem is 13.76. But I don't know what the sample size is, and I need to solve for that. So guys, if I can solve for this, life is good. So guys, first thing I want to do is I want to divide this side over here by 1.08032. So obviously I have to, so those things are going to go away. So on the left hand side, I get 1.05 Now, next thing I want to do is I want to multiply both sides by the 1.08032. So these are going to cancel over here, right? Now you're probably wondering, why are you going into so much detail and not just going ahead and simplifying things? Because I don't want to yet. I'm trying to teach you something. Now, next thing I need to do is I want to come in and I showed you a trick not long ago. If you watch the videos, it says that if we have a proportion equal proportion, that if I have a value in the numerator of the first fraction and a value in the denominator, I can switch those. So I can put the square root of n up here, and I can put that 1.05 down here. Now, it should be pretty clear to you that to solve for n, we're going to want to square both sides. So n is going to be equal to 13.76 times 1.08032 over 1.05 squared. Now, can we put that in our calculator without doing something goofy? I think so. Yeah, it's not going to work. All right, so I want 13.76 times 1.08032 divided by 1.05, and then I want to square all of that. Now I get 200.43, and I told you earlier, always round up when you're solving for n, which would be 201. Now, you may be wondering, why in the world did you make that so hard and not just put this in your calculator and round up? Why did you do all this? Well, the reason I did all that is I wanted to show something to you. I wanted to create something for you that can be used in the future. This value that we ended up with down here, is there anything that we can do to learn from this calculation when solving for n for a desired margin of error given information? Well, yes. We can go in and see that for future problems, we don't need to do all of the algebra that I did up here. We can just use this as a created formula. Now, in this problem right here, what was the significance of the 13.76? Wait a minute, I'm on the wrong problem, guys. Okay, lose my mind here. What was the significance of the 13.76? Well, the 13.76 was the standard deviation. What was the significance of the 1.08? That was our z critical. What was the significance of the 1.05? Oh shoot, that was supposed to be 1.50. Daggone it. Well, pretend. Okay. Pretend that was 1.05. What was the significance of the 1? Did I use 1.05 all the way through? Did I have a bozo moment? Nope, I said a bozo moment. Sorry about that. But what was the significance of the 1.05 right here? That was our desired margin of error. So guys, in your next problem, the one you have on your homework assignment, do you need to go through all of this? Starting with this? No, you don't need to do that. Let's say your population standard deviation is 16. Let's say you're doing a 95% confidence interval, and your desired margin of error is 0.21. Plug those numbers in, square them, round up, you got your sample size. All right, gang, that's it. That's all I got for you. Take care.